Okay, so last time we looked at the first way, the way using limits to derive the heat equation. Today we're going to be deriving the heat equation using the integral method. And it's very similar to the limit method. A lot of the logic and intuition behind it is very much the same. So we're going to have the same kind of scenario of a one-dimensional rod, and we're going to take a cross-sectional area, this time not from x to to x plus change in x, but instead from some arbitrary a and b, right? And similar to last time, we'll say that the rate of change of thermal energy over time is equal to the flux flux in and out over time plus the or yeah the flux or the heat energy transfer in and out over time plus the rate of change of any sources or sinks uh over time. uh and so now this time the way we write this is the rate of thermal energy. So thermal energy density, once again, is E, thermal energy density. And so we can get the rate of change of thermal energy over time by taking the integral of E times A dx from A to B, where actually, let me move this over, where E is a function of x and t, right? Position and time. Similarly, we can and then we can say that this is equal to the flux in, which is the flux at A, comma t, minus the flux out, or the flux at B, comma t, right? Thinking about it as like flux in, flux out, which we should multiply by A, or sorry, which we should multiply by A, and then plus the integral of the source times A times dx from A to B. And so you'll see here all the A's cancel out, which is why that was like redundant. But we're left with this integral equation, which we can now manipulate by noticing, oh, and I should say the rate of change of the thermal energy is equal to the change in flux plus the rate of change of any of the sources or sinks, right? Now, because time is independent of position, we can actually bring in the derivative inside, and we can say that the integral from A to B, this is the same as the integral from A to B of partial E partial t multiplied by dx, which is equal to, once again, the flux in minus flux out. Now we can actually, one more thing we can do is we can use the fundamental theorem of calculus to rewrite this instead as the integral from A to B of partial phi over partial x times dx, right? Because then using the fundamental theorem of calculus, you get the above expression. And then using the similar logic to the first term that we looked at, we can say that this can be rewritten as partial q over partial t times dx. And so this the reason we manipulated the expression like this is because now we can rewrite our whole statement as one. Oh, wait, I think there should be a minus sign here because since we're going from A to B, then this should be B minus partial B comma T minus A, but because it's not, we should put a minus sign to reverse it. But anyways, now we can rewrite this whole equation as the integral from A to B of partial E over partial T plus partial phi over partial X minus partial Q over partial T dx equals 0. And now the next transformation we have to do, one of the things you'll realize about integrals is that if we take the integral from some arbitrary value A to another arbitrary value B, and we say it's equal to 0, that means that the term inside has to also equal 0. The way to kind of make sense of that is to just think like, okay, let's say I have a function, right, that looks something like this. Or let's say we have a function which is a straight line. Now, it may be true that, say, from this A to this B, the area under the curve, the integral, is equal to 0 because these exactly subtract. But we want to generalize this to any A and to any B. So if A were here, for example, it would be a positive integral value. And so this statement would not hold true, right? The only way that a function can have the integral from any arbitrary value of A to B be 0 is if it's equal to 0. That's the only way then that from any A to any B, the area under the curve could equal 0, right? And think about that for a sec. But we can use that logic to now rewrite this equation as partial E over partial T plus partial phi over partial X minus partial Q over partial T equals 0. And you'll notice how this is very similar to the equation we were looking at before. And if I just manipulate the terms a little bit more, is equal to minus partial phi over partial X plus Q. This is the equation we started with way before, and we can then plug in what the equations we created for E and for phi to be able to then get it in terms of temperature. And so this is the second way using integrals to derive the heat equation. I'm not going to do the rest of the derivation now, plugging and chugging those values, but you can see where this leads. And funny enough, the reason that the logic being used here, you'll notice, is very similar to the same kind of proof for the first method, and which for the first method, but it uses integrals instead, which is but comes to the same solution. So yeah.